the board. So if you missed a word, that's fine. I just realized I forgot to start this. All right, so physics is the study of matter, energy, and how they are related. Can you guys see this purple? Or is this marker too light? You can see it? Okay. Oh, it's getting lighter. Okay, we're going to try switching colors. Okay, so it's the study of matter, energy, and how they are related. Okay, so physics really does kind of cover everything. One of the previous physics teachers, Mr. Wittenborn's favorite quotes was, everything is either physics or stamp collecting. I would like to say that stamp collecting still involves physics. So, yeah. All right. So, matter is everything that we can see, right? Everything we can feel, everything we can touch, even things that we can't see. So we can't really see the air, right? Yeah, we can feel it though, so we know that it's there. Energy, that's going to be like the energy that's flowing through our electrical wires, or the energy that's radiating from these light bulbs that gives us light, right? So we're going to talk about matter, we're going to talk about energy, but the biggest part with physics is talking about how they're related, okay? So when we talk about how they're related, that's when we're going to talk about things like when we apply a force to something. So if I apply a force to this beaker of water, it's blue for advanced physics. So when I apply a force to this beaker of water, it's going to move, right? So we are exerting energy to apply a force, and we're causing matter to change. Does that kind of make sense? And that's what physics studies, okay? Before we get into that too much, I do want to take a step back and look at science as a whole, okay? Like I said, physics is the basis of science, okay? It kind of is the underlayer, and chemistry and biology, astronomy, all of the other sciences are built up on top of it, okay? When we look at science as a whole, science studies the natural world, okay? As I said before, kind of with physics, it's the things that we can touch, the things that we can see, the things that we can record, okay? Make sense? Now, our culture says that that's all there is, right? Physics or science can study everything that we see. That's a lot. But it can't really explain emotion, okay? It can't really explain our full thought patterns, okay? We can get into, if you have more of this hormone or chemical or something like that in your bloodstream, it can affect your mood. We can get into that. But we can't explain everything behind thought patterns, okay? And that's where we take a step out of science into the realm of philosophy, okay? Philosophy is very similar to science in the fact that it is a study of something. There are rules to how we study it. There are reasons behind why we study it like we do. Philosophy is not something that is talked about near as much in today's day and age, even though there is a lot of philosophical ideas that are majorly influencing our culture. As a good scientist, you should not ignore the fact that we do need philosophy as well, okay? Philosophy and theology kind of pull together. Since we're a Catholic school, I do want to also bring in theology into that side of philosophy, okay? We live in a culture where there is no acceptance of one thing is true over another thing, right? what's true for you is true for you, but it might not be true for me. You've probably heard that said. Maybe not quite exactly in those words, but at least stated maybe in different words, right? Okay? Philosophy, by its very nature, takes a different approach. Philosophy is the search for truth. And using logic and reasoning, you are trying to find that truth, trying to find what is the proper thought process. Okay? Does that kind of make sense? So it's really interesting to look through philosophy. I'm guessing Mr. Vaughan will probably talk about this a little bit more in theology, because he really likes philosophy quite a bit. That's why he's a philosophy teacher too. But it's really interesting to look at some of the famous philosophers of each time and see how their works have influenced the course of human history. Because some people can say that Aristotle doesn't matter anymore, he was a long time ago, but his writings are still pretty true. There's still a lot of truth in them, and some might say there's a lot more truth in them than some more recent philosophers, okay? One thing that a lot of people really like to push nowadays is that philosophy is its own thing over here, and theology is another thing over here, and science is completely and totally separate from all of them, and probably the only thing that really matters. Okay? As Catholics, that is not what we believe. There are actually a lot of Catholic scientists that are very Catholic and very good scientists. Okay? I know I went to U of I. It is a large university. It is a very well-known university for engineering, for sciences of any type, so physics and chemistry especially. Biology, they did have a very large microbiology department, but not so much general biology. The whole time I was there, I was in completely secular classrooms with professors that may or may not have been Christian, but never mentioned their religious beliefs. Okay? I never once found anything in all of the classes that I took that disproved anything that I had learned in my religion or in the Catholic faith. When you really start looking into the Catholic faith side, so coming from the theology side towards science, it is actually very open. Okay? The, I guess, best way to state the Catholic Church's view on science is the study of the natural world. Okay? We're studying all the things that we can see. If we are coming from the true belief that God created the world, how in the world can studying what he created lead us away from him? Right? And that is the stance of the Catholic Church. So, there are a lot of religions, especially Christian religions, that say that evolution couldn't have happened, right? Because it doesn't align with the Bible. That is not the stance of the Catholic Church. The Catholic Church says, hey, when the Bible was written, people didn't always take everything literally. So could it have been a story that has some other truth other than the world was literally created in 7 days? Probably, right? That doesn't mean that it doesn't contain truth. It's just that that truth is not that literal truth that we see right in front of us. Does that make sense? Okay? And if you guys are not Catholic, I'm not saying that you guys are wrong or anything like that. I'm just explaining the views of the Catholic Church. Cool? Okay. The Catholic Church as a whole is very open to science. You guys have probably heard of the Big Bang Theory, right? If nothing else, you've heard of the TV show. Yeah? The guy who is actually now credited with being one of the main people who came up with the Big Bang Theory is a Catholic priest. He's the guy on this poster right here. Okay? George Lamartine. Okay? The Big Bang Theory actually is a very good scientific theory. It's probably the best one we have now. String theory is another one. I don't think a Catholic priest was necessarily involved in the coming up of that one. There's still a lot of problems with string theory. You've probably heard that word tossed around. We might talk about it on a Fun Physics Friday if you guys want. It gets really confusing really fast because it requires there to be at least 11 dimensions and some weird stuff like that. So the Catholic Church actually, when they saw that their image with science, especially with some of the stuff with Galileo and stuff, went down, and people started thinking that the Catholic Church was very negative against science, they actually started an observatory. They have a whole group of priests, sisters, lay people who work with the church, that their whole focus is actually to study science, to do good science, for lack of a better word. That is their whole job. They have an observatory right on the outskirts of Rome, but you need some certain conditions for an observatory to work really well. And unfortunately, over the years, Rome has expanded to the point where the light pollution from the city, do you guys know what light pollution is? Some of you do. So if you live in Cape, right, and you've ever been over in Southern Illinois at night and driving back over the bridge, like if you were coming to visit somebody, over in Southern Illinois, there's not a lot of lights, right? It's a lot of farmland. There's a few houses, but there's not a lot of lights. As you drive over the bridge, you can actually see kind of a glow in the sky over Cape, okay? That's from all the street lights, all the house lights, and all the lights that we have in our town. That is what we call light pollution. Does that kind of make sense? Okay. There's a lot of different things that we could talk about with light pollution. I don't want to get into it too much. It actually can mess with some nocturnal animals and stuff. You guys might have noticed that they've replaced some of the street lights in Cape. Yeah, and they're very white now. You know what I'm talking about? Yeah. Those are actually lights that are specifically designed to reduce light pollution. So if you look at the old ones, they kind of sent a glow all the way around the light, and the new ones focus it down quite a bit. So all of the light goes down onto the concrete instead of up into the air. So those have less light pollution. Anyways, back to what I was talking about. So we were talking about the observatory. The city of Rome, I think it's Rome. It's one of the cities, I believe. I need to double check that. It grew out to the point where even though this observatory was on a mountain, there was too much light pollution for them to be able to actually see the observatory well. Okay. So they actually have moved the observatory, and it's actually in Arizona right now. So there's some really cool people that work there. I'll probably show you guys a video on Friday of Brother Guy Consolongo. His name is Guy. It's spelled G-U-Y. Kind of interesting. But he has a degree in astronomy from MIT, and he is also a Catholic priest. And he has some really good explanations for the church's views on science and how science and reason are not at odds to each other. Cool? Do you guys have any questions so far? Have you talked about this in one of your science classes? Most of the freshmen say they haven't. So before we go on and get a little bit more into what is physics and things like that, I did want to point out this quote on our wall. This is from John Paul II, and it is a good sort of lead into how the church feels about science, okay? So it says, faith and reason are like two wings on which the human spirit rises to the contemplation of the truth. So the church's view is not that faith and science are at odds. It's actually of the view that they have to work together for us to truly understand what the world was created for, who God is, how he created the world, okay? Because we view it as the standpoint of, we started with this before, if God created the world, how can studying it do anything but lead us towards him? Another way that I've heard it put is, if you are somebody who creates something, you're going to leave somewhat of your mark on it, right? So if you paint a picture, even if you're trying to paint a picture of the same thing, every person in this room's picture is going to look a little bit different, right? Okay? Somewhat of your personality, somewhat of who you are goes into what you create, okay? So we can kind of use that analogy with the world. If God created the world, right, there should be somewhat of an indication of Him in what we see in the world, right? So if we look at it as a whole, we see something that is growing, that is thriving, that has a lot of beauty in it. And so we can use that as somewhat of an indication to see what might God be like, right? Okay, so that's generally the view of a Catholic scientist on these things. As I said before, if you're not Catholic, I'm just explaining the Catholic view on this. But yeah, do you guys have any questions? No? Okay, cool. So we talked about the study of matter and energy, how they are related, and that's physics. We got into the difference between science and theology. I do want to make it clear that there are things, like I said, that science doesn't necessarily study, okay? We talked about where the edge of science is, where philosophy begins, and theology fits in there as well. Do you guys have any questions? Yeah? Okay, cool. So now that we've talked about what physics is, right, what science is, we need to kind of talk about how we're going to go about studying the natural world, okay? How much time do I have left? We've got like 1 minute. Okay, I don't want to get into this if the bell's about to ring. So. Oh wait, no, that's the wrong. Oh, okay. I was looking at the wrong one. Thank you, Mr. Garner. All right. So, you guys have probably heard of the scientific method before, right? That one you have heard of. Yeah. My guess is in most of your grade school science classes, you talked about that pretty much every year, right? You probably had to memorize the steps every year. Yeah. So we're going to do it a little bit differently in this class, okay? I am a scientist who worked in a lab, and there are times where you do need to write down your predictions. You need to write down what you think is going to happen. You need to do that research and write down your data. You need to do that data collection, okay? You need to have a conclusion at the end. Was my prediction right? Was it wrong? Okay? But it is very rare, if you are working in a real lab setting, for it to be completely and totally linear. Okay? Kind of make sense? So I'm going to give you an example of what it's a little bit more like to do the scientific method in a real lab. Okay? So we're going to start with a scenario. You guys ready? Okay. We're going to pretend that you all just turned 16. You just got your license, and it is the first day that you get to drive yourself to school. Exciting day, right? Yeah. So you're getting ready. You've got your nice outfit on. You're ready for school. Your uniform's all, your shirt's tucked in, everything like that. And you go to grab your keys, but you're so excited, you knock them behind your dresser. Okay? What are you going to do? You might start by moving the dresser, but what if you can reach them? What if they're just like right behind the dresser? Yeah, you're probably going to try and grab them first. And then if you can't grab them, move the dresser, grab your keys, move your dresser back, go to school, right? You just went through the scientific method at least twice. Okay? So let's kind of break it down and explain all of those steps. Okay? So you started with your problem. You need to go to school. You need to have your keys to go to school. You knock them behind the dresser. Right? Yeah? So you have your problem. You've stated your problem to yourself, probably subconsciously. You didn't really think about it. Okay? We can take this either two ways. We can say that you looking to see where your keys were is either your research that you did, or if you try and reach back there and get them, that's the first test of your hypothesis, because you said, hey, I think I can reach these. I'm going to try and reach these and then pull them out, see if it works, right? So if you can't reach them, you have now finished the scientific method and you have made a conclusion, right? Now, you haven't solved your problem, right? So we need to go back and try another solution or create another hypothesis for how to reach those keys, right? Okay, our hypothesis was move the dresser, okay? Then you can reach the keys. So you move the dresser, you test it, you are successful, you now have a positive outcome, you move the dresser back, and we're good. Does that make sense? Yeah? So that's a little bit more like what the scientific method looks like in the lab. Like I said before, there are going to be times where you need to write out your hypothesis, write out your problem that you're trying to solve. But if you are working in a professional lab, you're going to be trying to get people to fund your research because research is really expensive. So you have to do a lot of research beforehand, right? You have to write a proposal. So you already have to have this experiment laid out and what you plan on and what you think is going to happen before you can even get into doing the experiment. Okay? Cool. In this class, we will kind of bridge somewhat between the sort of lab setup you guys knew in grade school and the lab setup that would be in more of a professional lab. Okay? I don't want to throw you guys in immediately because it can be a little bit of a floundering experience. But I do want to give you guys at least a little bit more freedom on some of your labs. So there's going to be a lot of labs where I say, hey, we need to test this thing. So maybe it's friction, okay? I want you to see how friction behaves on these different surfaces. Or friction depends on the weight in your cart or something like that, okay? But I'm not going to give you a list of you need to test 500 grams, 600 grams, 700 grams, okay? I'm going to let you pick that. Obviously, it's going to be constrained by the number of weights that'll fit in your cart and things like that, but I'm going to let you pick that. So you're going to have a little bit more freedom. Sound good? Yeah? I do need you guys to know that the scientific method is a laid out plan for how to solve a problem. I will not ask you guys to just list the steps. Okay? Good? You guys have any questions on that? Was this a little more fun than the way you went over it in grade school? Okay, good. All right, so that's the scientific method. All right. Let's see. Okay. So, like I said, we're still going over some of the basics. Okay, so we've talked about what science is, what the scientific method is. Next, I want to talk about models. Have a good afternoon, Mr. Ryan. Okay, so models. We need models to talk about science effectively. Okay. When I say models, what do you guys think of? A supermodel, definitely a model. Okay. Anybody else? Yeah. Pictures. Pictures are great models. Anybody else? Yeah.
A statue or something.
A statue. That would be a good model. Yeah. Yeah.
I kind of imagine what it is like in the solar system.
Yeah. Those are definitely good models. Okay. So we have a lot of models, right? You've probably used models. A lot of times pictures that you see in your grade school textbooks are things like the water cycle. You've probably seen that one, right? Yeah. You've probably seen models of atoms. You've probably seen models of cells, right? I want to go through some of the technical stuff behind models because models are very, very useful and they're very, very good for conveying scientific knowledge. they, just like science, have some limitations. Okay? So, I do want to write a definition of models. I'll try this one. Make sure I spell this right. You guys will find out as the year goes on. I am pretty good at science and math, but I am atrocious at spelling. So if I misspell something on the board, just tell me. I'm not going to be like Miss Ha and give you bonus points because you would all have A pluses in this class. So, all right. Models are some representation of another object. So we could have pictures, we could have statues, we could have videos. Videos are becoming far more common now. Okay, so animations, things like that. Anything that falls into that category of representing something is a model. Okay, so models represent another object. Okay, so they represent another object.
What were some of the examples again? Like pictures, videos?
Pictures, videos, statues, so 3D models. What were some of the other ones? Even now we can get into like 3D printing models and stuff like that. Animation is becoming much more common. Just because a moving animation of something, you can get a lot more information from than just a standard picture. Okay, so they represent another object. So the model is not the thing itself. Okay, so if I showed you like the picture over there of pistachio, that would be a model of pistachio. If I brought pistachio into the room, she's not a model because she is the thing. Good? Okay. So it represents another object. It gives us very important information about the object. Okay. But because it is a model, there is always going to be something that is incorrect about it. Okay. So like I said, there's always going to be something that's incorrect about it. Now, this thing that is incorrect can actually be really helpful if we know that it's not correct. Okay? A great example of this is the globe. Okay? Can anybody guess what might be incorrect about the globe? Yeah, the size. If this were the size of the Earth, would it be near as useful? No. Right? But we know that the Earth is not this size. Okay? Does anybody see anything else that might be incorrect? Yeah, the color. Okay, the color. If we look at this, so Missouri is yellow. If we look outside, is Missouri yellow? Yeah. Okay? So the color on this globe is not correct. But the color is showing us something else, right? It's going to show us the states in the US and different countries around the world. Okay? Good? So these inaccuracies in our models can actually be helpful for showing us different things. Okay? But that being said, we need to know that they're inaccurate. Okay? So I like to use page 7 in your textbook to show this. I'll hold it up so you guys can see. All right? So page 7 has 3 different models of the atom on it. Okay? It starts from oldest to newest. Okay? The oldest one listed in here is called the plum pudding model. And it assumes that an atom is just a sphere, okay? And it's got some negatively charged stuff stuck in with the positively charged stuff. Okay? That by itself is not completely incorrect, is it? Okay, we know an atom has positively charged stuff in it and negatively charged stuff. We have slightly more sophisticated names and stuff for it, but we know that that's in there, right? Now, this model just says that it's all thrown in there together, okay? The reason why they call it plum pudding is the person who came up with it, I can talk, was an English scientist, and their sort of definition, or what they called pudding at that time, was a little bit more like what we would think of like carrot cake. Does that kind of make sense? So like if you eat carrot cake that's got raisins in it, right? That's kind of the model they were going with. Okay, so the cake would be your positively charged stuff. The raisins would be your electrons. Good? So they're all kind of mixed up together. There's really not a whole lot of order other than they're kind of spread out. Okay? You guys have probably seen the next model. Okay? This was the one that came after it. Because there's a lot of inaccuracies in this one. There's still some useful information, but a lot of inaccuracies. Okay? This one's the next one. This is where we discovered that the atom was actually mostly empty space. Did you guys know that the atom was mostly empty space? Yeah, it's actually like 90% empty space. Kind of crazy. The nucleus is really, really small. The nucleus in this picture is way too big, right? But for this model to be useful, we kind of need to see the nucleus, right? Yeah. So nucleus is way too big. But if we know that looking at the picture, this is still a really useful picture because it tells us, hey, the nucleus, all that positive stuff and all the neutrons and stuff are right there in the center. They're in a really tiny, closely packed area. Then the electrons are whizzing around all over the outside, right? Yeah? All right, so we've got this model and it's really useful. This is actually probably the model you will see more places than anything else, right? Anything that's mildly scientific, they're probably going to have this like as their logo or something like that. I think the Big Bang Theory has this on there, like scene shift, like the thing between the scenes. Yeah. Jimmy Neutron. This is definitely in Jimmy Neutron. Yeah. Now, this is the one that we use the most because it is a very useful model. This one is actually much more correct for what we know about the atom. Okay? Looking at it, it actually looks like it has less detail than that plum pudding model that we started with, right? Yeah? This one shows some different things. Okay? It still shows that nucleus in the center, so that's still your positive stuff sitting in the center with your neutrons that don't have any charge. But then there's this like faded blue circle around it. Okay? This is the model that reflects quantum physics. Okay? In quantum physics, there's some really weird stuff that goes on that says you can't actually ever know exactly where the atom or the electron is, and some weird stuff like that. We can get into that if you guys want to on like a Fun Physics Friday. It's has to do with Planck's constant, and there's like a set maximum speed that things can go. It gets really confusing really fast, so I don't want to get into that too much here. Essentially, what this is showing is that the electrons are somewhere in this area, and we really don't know where. Okay? Now, if you are somebody who's trying to figure out what this whole like orbital thing is and like how there's energy levels in an atom, is this going to be super useful? No. This one's going to be way more useful, okay? So this model that is more inaccurate is actually more useful. Good? So we can actually use these inaccuracies to our benefit. So it's not like probably how you guys learned in grade school, if something's wrong, that's really bad. Inaccuracies in models can actually be a good thing. Okay? Cool?
All right, I'm going through material really fast. I think last year this took me like 3 days to go through this much material.
You guys are good? Okay. I don't want to like leave anybody behind or anything like that. No questions? No? Okay. All right, so let's go to step 41. This is a longer lunch period, so you guys will probably be farther ahead than everybody else tomorrow. So you guys might get to watch an extra video or something. All righty. All right. I think we have time to at least talk about this. Oh no, that's not good. I'll have to fix that later. This is the inside of a clock. I just accidentally slightly broke it. I can fix it though. It'll be fine. I do want to kind of touch on scientific laws and scientific theories. You guys have heard of theories and laws before, right? You've heard of like Newton's laws of motion. You've heard of the Big Bang Theory, right? You've probably heard of things like E equals mc squared as part of a theory. One of the ones done by Einstein, okay? What I want to make clear is scientific laws and theories are not necessarily set in stone, okay? Especially when they're called laws, it definitely sounds like it, right? Because like if you break a law in like normal colloquial terms of like you're speeding or you break into a bank or something like that, right? Those are not quite on the same level as each other, but you know. So if you break a law like that, you're going to have some consequences, right? Yeah? Physics laws and physics theories are a little bit different, okay? They are describing what happens in the world. So in theory, you probably can't break them, okay? Does that kind of make sense? Because it's telling us what the constraints of the physical world are. Now, if you were able to break them, guess what happens to that law or theory? One thing about them is untrue. Guess what happens to it? Anybody? Yeah. It gets tossed out, or at least modified, because our theories and our laws are the best guesses that we had at that time that they were formulated. Okay? Now, there's a few laws, like Newton's law of gravity. We know it's wrong, but it's good enough that if we were just trying to figure out, I don't know, how fast a bowling ball was falling on Mars, we would use Newton's law of gravity because it's so much easier to use than Einstein's theory of general relativity, which is what is our best guess at what gravity is, but we actually already know that one's not 100% true, and we're still trying to figure out how to explain gravity. Okay? So laws and theories are our best guesses, right? There's been a lot of laws throughout all of history that have been tossed out, just completely tossed out because they were wrong, okay? They were made by people who didn't have good enough equipment to measure the necessary values to disprove them, okay? So they were the best guess they had. So there's a lot of laws that have been thrown out. There's a lot of people now who really don't like the term law. And that's why most of the recent things that we've created that are the same sort of type of thing are called laws or theories instead of laws, okay? The word theory kind of captures this idea of as soon as they're disproved, then they're wrong, better than the word law. Kind of make sense? That being said, it doesn't mean that something that's called a law is any stronger or any weaker than something that's called a theory, okay? If you look at your laws and theories, a lot of times you can kind of draw a little bit of a division between them. Most of the time the laws are pretty well always older. Theories are generally newer. There's a few older theories, but most of them are newer. You'll also find that partially because the laws are older, they're going to give you kind of a basis of, hey, I see this happen every time. So the law of gravity, Newton's law of gravity, pretty much says, hey, when I drop something, it always falls like this. Okay? Does that kind of make sense? That goes for planets too. When I see the planets move, I see them move like this. And we kind of put them together. Theories tend to tell you a little bit more of why. So, have a good day, guys.
Thank you.